In this video, we'll talk about motion under the influence of an ideal spring force, but now motion that also is under the influence of a resistive force. I know from Newton's second law that the net force is approximately equal to the mass times the acceleration in the classical approximation, where the speed is much less than the speed of light. And I know acceleration is essentially the second derivative of position. So in the x direction, I have the x component of the net force is equal to m times x double dot, where the two dots represent the second derivative of time. I can show you here. This represents the second derivative of x with respect to time. And that is what we call acceleration. Now, as I said before, here I will study the motion under the influence of an ideal spring force, and this is the ideal spring force. But I mentioned that I will also have a resistive force, and this second part, this is the force that resists the motion. And I will talk about why it resists the motion. So here, remember, x represents the position, x dot represents the velocity. Now, b is a parameter that is positive. Okay, so I will make a note. That's a positive parameter. And I have the minus sign in front of this term. Since I have the minus sign, this means that this force is always pointing opposite to velocity. If the velocity is positive, then the whole thing will be a force pointing in the negative direction. If the velocity is negative, then this force will be pointing in the positive direction. And this shows you that this force is always opposite to velocity. And that's why it is resisting force. There is no way that this will help an object, my system, to speed up. This will always cause the system to slow down. Now, I have written here some two more parameters that I will need. Omega squared, as usual, is defined as k over m. And I'm also defining the parameter veta to be b over 2m. And b is the damping parameter here that I have in my resistive force. So the greater the resistive force is, the greater b is, and that means the greater this parameter veta is. Now, combining, this is my net force in the x direction from the sum of the two forces, and this is Newton's second law. So what I'm going to do here, I will combine the two. Minus kx minus bx dot is equal to mx double dot. And if I rearrange things, I can have mx double dot plus bx dot plus kx equals 0. Now if I divide with the mass, b over m is 2 veta, and then k over m is omega naught squared. And this is now the differential equation that I have to solve in order to find the solution. And what would the solution be? Well, it's the differential equation I'm looking for this. Okay, if I know this, then I will know what the motion will look like. So when I say that I'm looking to find the motion of the object, what I mean practically, mathematically, is I need to find what x is as a function of time. Once I know this, then I will know the velocity by taking the derivative of x. I can find the acceleration by taking the second derivative of x, and so on. But at the end of the day, what I want to get is x as a function of time. Now, this is a second order differential equation. And you know from differential equations, if you can find, even by chance, you guess a function, and it turns out to be a solution to your differential equation, even by chance, then you found it and you can use it. So one thing that we can easily show is that e to the rt is actually a solution to this, and I can show you why that is the case. So if I have x of t e to the rt, then the first derivative of that will be r to the ert, and the second derivative of this will be r squared e to the rt. Now I can take all of these and plug them into here. Okay, so I'm gonna take these three and I'm gonna plug them into here. Let's see what I'm gonna get. So x double dot is r squared e to the rt plus 2 vita x dot r e to the rt plus omega naught squared e to the rt, and that should be equal to 0. Now, for the left side to be equal to 0, I need to have a condition. I need to have the case where r squared plus 2 vita r plus omega naught squared is equal to 0. And this is what we call the auxiliary equation. There is only one Now, this is a quadratic equation, and the two solutions to this are given by minus vita plus or minus the square root of vita squared and the other solution will be minus vita minus that Now let's call this one R1. Let's call this one R2. And then, since these are the two solutions that satisfy the auxiliary equation, then I have actually found two solutions. Since I said e to the RT is a possible solution, then e to the R1t will be one possible solution, and e to the R2t will be the other one. So these are two solutions that satisfy my differential equation. And now I can write the general equation, the general solution to the differential equation as a constant 1 times e to the R1t plus constant 2 e to the R2t. So this is what the general solution is to the differential equation. And let's make a note. This is the differential equation.